All right, Chem 11, our next topic, pH and pOH. And this links directly with the previous lecture on acids and bases. As you know from grade 10, pH, the pH scale, down here in the green, is what we use to measure the strength of an acid or base. So we're obviously talking about how to measure how strong or weak an acid or base is today. All right, same format as usual. Our course notes that we'd use if we were in regular classes are up here on the iPad. These are on your D2L site right now. And I'll use the rest of the whiteboard here for writing out notes or calculations or key terms or whatever it happens to be. So let's get into it. So what is pH? pH stands for portends of hydrogen. Remember, the language of scholars back when all this stuff was being figured out was Latin. If you went to university and studied stuff, you studied in Latin, right? So portends means strength, right? Some teachers say, oh, it means power. Yeah, I guess power to strength is the same, and power starts with P, but the original word was portends. So we're talking about the strength of hydrogen. And if I remember, hydrogen ions, or protons, were a key player here because acids donated them, right? And bases accept them. So hydrogen is a big player here. And we know that a hydrogen ion is a proton, all right? So the pH scale, like we have down here in the green, you saw this in grade 10. It runs numerically 0 to 14. 0 to 7 is the region of acids. And 7 to 14, that's the region of bases. And right in the middle, I don't have any room down here, I'll put it right here, 7 is perfectly neutral, neither acidic nor basic. Pure water is a pH of 7. All right? So acidic solutions here, alkaline or basic solutions are here, and hopefully you remember that from grade 10. All right? So let's go a little further here. The pH scale. So when we see the pH scale, it's 0 to 14, 7 is neutral like pure water. I'm just going to bring all this up so my hand's not constantly in the way. So on the pH scale, 0 to 14. 0 to 7, that's acidic. 7 to 14, that's basic. Now, neutral right in the middle. As I go away from the middle, so as I go 6, 5, 4, as I start going to one extreme, the 0 here, we get stronger and stronger in terms of being an acid. As we start at 7, which is perfectly neutral, and we start to increase and work away from 7, go to this extreme end of the pH scale, we become a stronger and stronger and stronger base. All right? You remember that from grade 10, I hope. So in terms of bases, these ones are weak and these ones are super strong. In acids, just on this side of 7 is weak, and on this side it's very strong in terms of being an acid. So our strongest bases and our strongest acids are at the far opposite ends of the pH scale. Strongest bases here around 13 and 14. Strongest acids around 0, 1, and 2 down here. All right? Now, the increments on the pH scale, there are 14 of them here. Every time you move one of these numbers, you're not becoming one more times, stronger, a little bit stronger. It's 10 times more, right? So each step in this is 10 times. So for example, if I have a base, right? I'll do it in a different color so it stands out. If I have a base and I'm right here at 10, and I want to compare, well, how much more basic is something at 13? So we go 1, 2, 3. So there's 3 steps. 1, 2, 3. So that's 10 times 10 times 10. And that means, if we look at it, it's 10 to the 3, so the 3 steps, and that's 1,000. It means that something with a pH of 13 is 1,000 times more basic than something at a pH of 10, right? 1, 2, 3 steps. Each of these is 10 times, so it's 10 to the third. 1, 2, 3. All right? So something with a pH of 13 is 1,000 times more basic than something with a pH of 10. Or we can say something with a pH of 10 is 1,000 times less basic than something that is 13. So you can compare it in one direction or the other. And it's the same for our acids as well. So we go to the acid side of things here and we look at something that is pH of 5. There's 5 there, we compare it to 1, right? These are both acidic. They're both on the low side of the 7, between 0 and 7. That's acidic. So how much more acidic is this? Because I know this is where my strong ones are, down here at this end. So we go 1, 2, 3, 4. And each of these is 10 times. So we've got 10 times 10 times 10, which is equal to 10 to the fourth. That 4 is for our 4 jumps. 1, 2, 3, 4. And that is 10,000. So something with a pH of 1 is 10,000 times more acidic than something with a pH of 5. Or we can reverse that and say something with a pH of 5 is 10,000 times less acidic than something with a pH of 1. This was explained to you hopefully in grade 10, but that's it. So each time we make a step on the pH scale, we're getting 10 times more or less, depending on the direction, acidic or basic. Again, depending on what side of 7 you're on. All right? So, and that's explained here in these last few points, kind of what I did here in the orange and pink. So, a pick of the pH scale here. See what I did with the pick? Anyway, so here's our pH scale, and I put this in here. We've got our green pH scale here right now. I put this in here because it shows many common substances, many common solutions in our house and in our environment, and it shows their, roughly where they fit in with the pH scale. So if you look here, ammonia, soapy water, bleaches, oven cleaner, liquid Drano, right? Drain cleaner. All of that stuff is very basic. And look up here where the pH is 0, 1, 2, 3, right? Look, lemon juice, vinegar, grapefruit, orange juice, soda, pop, tomato juice. All of that stuff, that's food, fruits and vegetables. Like I said in the acids and base lecture, a lot of our foods are very acidic. Now, we want to calculate pH, right? So I'm going to erase this quickly because we kind of got this stuff down pat. I'm hoping we remember this stuff from grade 10. Right? So far, pretty easy lecture, right, sir? Hopefully it stays that way. So, now if I look at the term pH, I'll bring this up, but we'll go over it here. If I look at pH, it's portends of hydrogen, right? So what pH measures, right, it's the H pluses that are released. And I'm thinking to myself, wait a second, who releases H pluses? That's acids. Bases don't do that. Bases accept them, right? This is a proton. A hydrogen ion is a proton. If pH measures how many protons are released, pH only measures acids, right? Think about it. If I put HCl in water, we saw this before, what happens? Well, this is my acid. Water is amphoteric. It can act like an acid or a base. So if it's with an acid, water will act like a base. This H was going to go over to here. This is an acid. It's a proton donor, and that proton will come over to the proton acceptor, which is the water. So I end up with Cl negative and H3O plus. Right? Another one. Here's nitric acid. And if I make up a solution of nitric acid, what happens? Well, this is a strong acid. It's going to dissociate into nitrates, these things, and those. And that proton is going to, again, join up with the base. This is nitric acid. The water is amphoteric, so if it's with an acid, it plays the role of the base. I'm going to get nitrate ions and hydroniums. If you remember, these are hydronium ions. We introduced you to that last lecture. Each acid, every acid, when you mix it with water, is going to give up H pluses, and those H pluses are going to go with the water. So every time, no matter what, if we put an acid into water, we're getting these hydroniums. The other thing, that's going to depend on the makeup of the acid. But one thing's going to happen for sure. Acids are going to release their H's. So these H's are going to say, see you later. They're going to walk, and they're going to join up with the base because the base accepts them. When water accepts an H, H2O becomes H3O. So one thing that will be formed every single time an acid is dumped into water are these hydroniums. All right? So if I look at a solution and I see hydroniums inside of it, then I know it's got to be an acidic solution. It could be a hydrochloric acid solution, or it could be a nitric acid solution. But the other thing will tell me if it's hydrochloric acid or nitric acid, but I know it's acidic as soon as I see this. So this is important. Every single acid gives up H's, they join to the H2O, and they form these. Every time I'm going to get this if I'm dealing with an acid or an acidic solution. All right? So when we calculate pH, what we actually do is we use the concentration of these, right? The more concentration measures how many of these are in a given volume, like a beaker or whatever, a flask. So the more of these that I have, the more H's had to be released. And the more you release H's, the better an acid you are, or a stronger acid you are, right? Let me go over that again. The more of these that I can count up, it means more of these H's had to be released. And what do acids do? They release H pluses, right? So if I'm releasing a ton of these, I'm going to form a ton of these. And if I release a ton of these, I'm a very strong acid. I'm great at being an acid because that's my whole identity, is releasing protons or H plus ions. So if I have a ton of these, it means I did my job really well. A ton of these are released and they mixed with the water to form these. All right? So our pH formula has hydronium in it. We count these up and we'll be able to tell how many H's are released because every water takes on just one H. So if I have 10 of these, I know 10 H's released. If I have 5,000 of these, I know 5,000 H's were released, right? So that gives me an idea of how good of an acid it was, giving away all those protons. The square brackets around it. So now that I've made that link for you, let's look at that formula. There's square brackets around the hydronium part of it, right? So if I look at it, pH is equal to negative log 10 of this, the hydronium ion, right? And we get this when H plus combines with water. And we know we get the H plus from this. So this measures, this is for acids only. All right? So, the squared brackets here, that means concentration. So the squared brackets means we're measuring the concentration. And the most common way to measure concentration is what? One of our earlier lectures. It is moles per liter. So whatever goes in here, which is the concentration of hydronium, it's going to be mole per liter of hydronium. All right? So my concentration in moles per liter of hydronium is going to go in that bracket right here. The pH scale is a logarithmic scale. It's to a base of 10. Remember, every jump was 10 times 10 times 10. So we got our logarithm here for this formula has a base of 10, which makes sense. And we're trying to find the pH. All right? So now the next step is to try to figure out how to use our calculator. Right? Now I've got some sample problems at the end of this lecture that we're going to work through together. So we'll work on the calculator thing a little bit later. And I've got a new friend to introduce to you as well. But in class right now, I'd put one on the board and we would really try to work it out because there's a little bit of a trick to it. And some makes of calculators, do this logarithm thing differently than other makes, right? So Casio calculators do things different than Texas Instrument, right? Then do things differently than Sharp. So we would be working that out. You will have to work it out by making sure your answers are the same as mine. So the next thing I want to talk about is pOH. All right? So up here, I'm going to mark acid. pH only measures acids. The pOH scale is only for bases. And I know you're still thinking, but sir, you just said before on the pH scale, 7 up to 14 is for bases. We're going to get there. Don't worry, we will get there. We'll do this in blue because bases turn litmus blue. Anyway, we know that a base is a hydrogen ion or proton acceptor, right? And if I put a base in water, what happens? Well, I know this is going to accept a proton. This is my base. That's my proton or H plus acceptor. Water is amphoteric, so it says, well, if you're going to be the base, I will become the acid, and I will give you, because acids are proton donors, right? So the water says, well, I'll give you one of my H's, because I'm the acid, and that's what we do. We donate, we give away protons. So when water does that, H2O just becomes OH, which is hydroxide. We've seen this polyatomic before, right, in grade 10. This is the hydroxide polyatomic ion. Well, if I take it, right, because water looks like this, and if it donates one of its H's and that one goes away, look what I'm left with. I'm just left with OH, right? And so water donates the H, and ammonia becomes ammonium. Correct? So this happens every time we put a base in with an acid, right? The acid will donate. But now if we have a basic solution, what happens? Right? In that basic solution, what happens is the base steals from water and the water forms OHs. Right? Whatever the base is, it takes H's from, well, the only other thing in the solution, which is water. Right? So this is like our hydronium here. Right? So this gets made every time a base interacts with water. All right? So basic solution, we use pOH because we're measuring the power or portends, the strength of the hydroxides. All right? So let's take a look at this. So the formula for pOH is this. pOH is equal to negative log 10 of the hydroxide polyatomic ion. Again, bases always make this. When I put a base in with water, it steals or accepts, right? It accepts a proton from the water and leaves this behind. A base that is a really good base accepts lots of protons, which means lots of water are going to lose their protons to the base, and we're going to have lots of this left over from the water. The more of these I have, the more protons were accepted from the water, which means the base was a better job. It was better at doing its job of being a base, and it's a stronger base. If I have a ton of these, then a ton of these are accepted, and this is doing its job really, really well, so it's very strong. If I only have a few of these, only a few of these were accepted by the base, and the base isn't all that great at it. All right? So again, the squared brackets tells you it's a concentration, and what it is, it's the concentration of the hydroxide polyatomic ion in moles per liter. Again, molarity is the number one way of measuring concentration in chemistry. So the calculator, again, we got to use a calculator thing. I'm going to show you how mine works. Again, I can't say for sure how yours works. So you got to go through and push the button sequentially to get the same answer as me and then remember how you did that. All right? So the pH scale only works for acids, apparently. And the pH scale, or the pOH scale, only works for bases. So why do we have just one scale? Why do we have just the pH scale? Why have I never heard of this before? Right? Well, here's the thing. We can easily convert this into this. Right? And here's what I'm talking about. In both scales, I'm going to erase this. If I were to draw both scales next to each other, it would look like this. Right? Here's our pH scale in red, and we know that that's good for acids. Being number one is the best. If the pH scale is for acids, these are the best acids, 0 and 1, down in this area. These acids are weak. You really suck at being an acid if you're here, right? You're so terrible at being an acid, you're actually a base. Now look, if I were to take the pOH scale and put it in the opposite direction, the strongest bases, because being number one is the best, the strongest bases are right here at this end. And again, as you go up to 14, weaker bases here, and then you really suck at being a base if you're here. Well, I really suck at being a base because I'm an acid. The two scales run in opposite directions of each other. So if I'm a 1 on the pH scale, that means I'm a really, really strong acid. Right? Being number one means you're the best. I'm one of the best acids out there. Well, are you a base? No, I suck at being a base. I'm like 13. Right? I'm really terrible at being a base. I'm not a base at all. And look for bases. If I took a really, really strong base, right? Like the drain cleaner. The drain cleaner's right here on the pOH scale. The blue scale is pOH. Right? It's amazing. Being number one is the best. Drain cleaner's here. Its pOH value is 1. Now, if I relate that to the pH scale, it's at a 13. I'm wicked at being a base, but I suck at being an acid. I'm no good at being an acid at all because I'm an incredible base. And so the relationship between the two is, if we add up the values for any substance, its pH value and its pOH value, they equal 14. Right? So look at it this way. Let's take that really strong acid again. Its pH is 1. Super strong acid. It's amazing at being an acid. It's really, really sucky at being a base. Well, that's because it's a great acid. So look, it's a 1 here. It's a 13 on here. 1 and 13 is 14 when I add them together. What about something that is a mediocre base? Say a 4, right? The pOH scale is for bases. 4 is, you're okay, you're doing an all right job being a base, right? So you're 4 here, you're decent, you're a pretty good base. On this scale, the acid scale, no, you're not that great at being an acid, dude. Well, I'm not an acid, I'm a base, I'm the opposite. But the 4 lines up with the 10. And 10 plus 4 is 14, just like 1 and 13. If I have water, water's pH is 7, its pOH is 7. So 7 and 7 is 14. 8 and 6 is 14. 2 and 12 is 14. So this is how the pOH scale relates to the pH scale. So if I know this scale, for example, if I know a base has a pH of 11, I know its pOH is 3, because 11 and 3 equal 14, right? So I don't need this one. I just have this one, it covers everything, right? If I have an acid with a pH of 3, it's a medium strength acid. right? If I have a base and it's a 13, I know that's a pretty strong base. And it's pOH. If its pH is 13, I know its pOH is 1. And being number 1 or 0 to 1 is the best. So this is a very strong acid. I don't need a second scale to clutter up my notebooks in that with. I can use this one. All right? So this is the pOH scale. And so every solution out there that has a pH has a corresponding pOH. And if I take those two numbers together, they add up to 14. If I can find one, I can easily find the other because they must add up to 14. All right? This is a lot easier on the calculator to do than that logarithm stuff, trust me. So, I had some problems that I wanted to put forward to you. They are on the website. Let me bring up those problems really quickly. Stupid sir. Come on, interweb, let's go. Should be like playing some Jeopardy music or something right here now. All right, we'll reload that up because I reloaded it since I put it on this iPad here. I forgot that I did that. So let's quickly download this thing. Should be playing some elevator music for you or something. All right. So we'll get up to the practice problems. They should be on here now. There's our practice problem right there. Perfect. Sorry about that wait, guys. All right. Don't need that anymore. The first practice problem says, and I'll work it out here exactly the way that I need to see it on your notes. Now, I know we are used to seeing the Calculator-O-Matic 3000 solar powered edition. That doesn't have a logarithm button, so he can't come here today. Instead, I have his little brother, the Calculator-O-Matic 4000 solar powered edition. It's genetic, the solar panel, so the little brother obviously has them as well. Runs in the family. So even when the aliens come down and take out the power grid, this guy's still doing chemistry. Anyway, so we'll turn that on. I need this button right here. I don't know if you can see it, the logarithm button right here. I need that. And my exponent button is right here. I need that to do these problems. All right? So, our first problem. What is the pH? What is the pH? This is number 1. What is the pH of a phosphoric acid solution? Phosphoric acid is H3PO4. That has a hydronium ion concentration equal to 0.034 moles per liter. All right? First thing I start out with is my formula. My formula for pH, because that's what I'm asked for. pH is equal to negative log 10. Show your formula. Do not throw away marks. So there's my formula. I rewrite it. Now I sub in the value. Right here, this is my moles per liter, so that's my concentration. And so on my calculator, now this is how mine works. It doesn't mean yours works this way. What I have to do on this one is I hit log. And it shows a little bracket here next to the log thing. I don't know if you can see this. And I type in 0.034. I don't need moles per liter. I close the brackets and hit equals. Just say enter. And I can see that I get a negative number. Now, negative is a positive. So my pH is equal to 1.468. So 1.47. And that is my $1 million correct answer right there. So that's all it's to it. Now, what you are going to have to do, I'll move this out of the way for a moment. what you're going to have to do is get your calculator and figure out how to use the log button with this value. Don't forget to put the zeros and the decimal points in there. That's a common mistake. People go 0.34 instead of that. They'll forget that 0. Figure out how you got to use your log button and this value to get this answer. And then remember that. All right? There's the answer number 1. Pause the video. Copy that down if you need to. I'm going to move on to number 2. Number 2. Number 2 is, what is the hydronium ion concentration? So what is the hydronium ion concentration? So I'm looking for this. There's my hydronium ion concentration. I don't know what it is. Of a nitric acid solution that has a pH of 2.5. 2.50 actually. All right, so again, negative log 10 H3O plus. And now I'm given the pH. So 2.5 goes here, and that's equal to negative log 10 of this thing. Now, weird thing happens. Basically what happens is this. Our concentration of this, when you bring this over with a logarithm, it becomes 10, because our base is 10, to the negative exponent of this thing. So that 2.5 becomes my negative exponent. And so I put 10 to the negative 2.5, and I'll get this. And I'll write both answers because your calculator, depending on how it's set up, will give you one or the other. It'll be either this, so the expanded version, 0.00316 moles per liter, or your calculator will give you the scientific notation, 3.16 times 10 to the negative 3 moles per liter. Both of these are the same number. Both of those are correct. All right? So when we're given the pH value or the pOH, we just make it a negative exponent to the 10th, to the base of 10, and that will be our concentration in moles per liter. All right? Copy that down. Pause the video if you need to. I'm going to do another problem. Oh, Macy the Wonder Dog. Little crazy. Our third problem. Our third problem says, what is the pOH of a lithium hydroxide solution that has a hydroxide ion concentration that is equal to 0.0076 moles per liter? All right? So, first thing, I'm going to use my pOH formula this time. All right? And so, negative log 10, because I've been given hydroxide, I use pOH. LiOH, lithium hydroxide, is a base. I have to use the base one, right? Like that. So, pOH is equal to negative log 10, and I put in this value. And my pOH, again, use your calculator, and your answer should be 2.12. All right, so that's A right there. And part B I'll do in red. B is, well, what's the pH of that same solution? So I know that pH plus pOH equals 14. So that means my pH, when I add it to 2.12, it'll equal 14. Now, to cancel that out, what I do is it's plus 2.12, I subtract it on both sides, right? And what will end up happening is these will cancel, and pH is equal to 14 minus 2.12. And when I subtract that, my pH is equal to 11.88. All right? 11.88, and that is my $1 million answer for B. There's my $1 million answer for A. Easy enough? I hope so. Pause the video if you need to get that down. We got one more problem. We'll get it in really quickly here. All right, our last problem. It says, what is the pH of an aqueous solution of calcium hydroxide that has a concentration of 0.04 moles per liter? Now, notice the wording on this. It doesn't say hydroxide concentration. It says calcium hydroxide has the concentration. So this concentration is of this. It's not of hydroxide. I can't put this into pOH right away because this value is not for the OHs. It's for the calcium hydroxide. And if I look at it, if I have one of these molecules, I have 2 OHs. If I have 10 of these, I have 20 OHs. Every molecule has 2 OHs. So what I actually have to do first here is I got to take the moles of this, because this is how many moles of this are in 1 liter, moles per 1 liter. So I'm going to run this little side calculation. And we've done this before. So I take the concentration of my calcium hydroxide and I multiply it by 2 moles of hydroxides for every mole of CaOH2. These cancel, and I end up with the moles, or the concentration, or at least the moles of this. Now, that's how many moles are in 1 liter. This is how many moles are in 1 liter. So my concentration for the OH is 0.08 moles per liter. This is what I'm going to put into my pOH. So this step right here is an extra step. So now I take this value and I use my pOH formula. And pOH is equal to negative log 10. I use this value, not this one. This one right here. And my pOH is equal to 1.1. Now the question asks, what is my pH? But I couldn't do pH because I had these, a base. It gave me a base, so I had to find this first, right? There's no hydroniums involved here. So I had to find pOH because the thing that was in here gave me OHs. But I now know I can take this and do the last part of the calculation and say that pH plus pOH equals 14. pH plus 1.1 equals 14. And therefore my pH is equal to 14 minus 1.1. And my pH is equal to 12.9. And that is my final $1 million answer. Oh boy, that's a lot. I'm going to put a worksheet up for you on the D2L page. I'm also going to do a problem solving session for a bunch of these, because these can be simple but tricky at the same time. All right? So review these problems and see if you can understand this junk. All right? No, I'm just kidding. It's not really junk. It's important stuff. Anyway, hope it was crystal clear. If you got any questions, comments, or concerns, throw them into the comment section below this video. Or if you're one of my students, reach out to me through the EDSB page. Sooner rather than later. Don't let it wait. If you don't know, raise your hand or reach out. Can't just sit there and not know. Talk to you soon. Bye-bye.